Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In my previous video in this playlist, I introduced the notion of a smooth manifold, where we put differentiable structure on topological spaces. And what do we mean by differentiable structure? That's structure that allows us to talk about concepts from calculus, concepts including things like tangent spaces. So we saw how to talk about tangent vectors on smooth manifolds, but unfortunately the definition there was a little bit unsatisfactory. And why is that? Because the definition really depended on which coordinate patch you were looking at. And what we did instead was we immediately showed that it doesn't matter which coordinate patch you use, those tangent spaces, which are different, can be identified in a canonical way. What I want to show in this video is to come up with a much more intrinsic way of looking at tangent vectors and hence tangent spaces. And in so doing, that will also allow us to talk about a new type of structure which incorporates a lot more geometry, so the geometry of distances, and that's the notion of a Riemannian manifold. So that's extra structure again on top of that of a smooth manifold. And to do that, I'll need to talk about the notion of smooth maps. So in fact, the point of having a differentiable structure is so that we can talk about the notion of smoothness of maps. And this is actually a general theme in mathematics. For example, why do we put a vector space structure on certain sets, okay? If we put a vector space structure on certain sets, it allows us to talk about a linear map between them. Why do we put topological structure on sets? It allows us to talk about continuous maps between them. Or in the case of smooth structure, putting a smooth manifold structure on a topological space allows us to talk about when a map between them is actually smooth. So that's where I'll start. Okay, so let's suppose we have two smooth manifolds, X and Y. To be smooth manifolds, that means that they look locally like Euclidean space. Okay, so they have smooth charts. So X has smooth charts. Suppose it's an union of open sets VI, and these VI's are homeomorphic to unit n balls, B and I, and the homeomorphism is given by phi I, and basically the differentiable structure on this VI is given by the differentiable structure on this B and I. Okay, so that's the smooth chart for X, and we have another one for Y, and that's given by the coordinate patches psi j, and this is an m-dimensional manifold, so you use the unit m ball here, and you have homeomorphisms of them, or copies of them, with open subsets of Y like that. Okay, so that's the picture that we have here. Here's our X, here's our Y. Okay, and this is a union of these VI's. This is a union of these WJ's. And let's suppose we want to talk about a map between them. So let's put a map there. That's our F. And we want to ask, when is it smooth? Okay, well, as is suggested from what happens in the Euclidean case, to say when it's smooth, I guess you just need to say what does it mean to be smooth at a particular point. Once you have that definition, to say you have a smooth function just means it's smooth at every point. So here we'll just give the definition of what it means to be smooth at some particular point, say P. And let's suppose that point P is inside this open set VI. Okay, so if you have a smooth map, well, certainly it should be continuous. So the starting point will be a continuous function from X to Y. Okay, and we'll say it's smooth at P when. Okay, so what's that extra condition? Okay, well, that's easy enough. So remember what the basic idea of this differentiable structure is. So basically, this VI, you identify with this unit ball in terms of the differentiable structure. Let's suppose this P gets mapped to this open set WJ. So f of P is in there. That's f of P. Right? Now you can identify this neighborhood of f of P with this WJ and hence with this unit ball here. So what you can do is you can map basically, these are homeomorphisms, and this is a homeomorphism. So essentially, what you can do is you can look at the composed map from here to here to here to here and ask that it is smooth in the point corresponding to P. Okay, and what's the corresponding point to P? Well, I guess you pull it back up to here. It's phi I inverse of P. Okay, so to make this work, okay, you just basically go down, across, and take the inverse of this. So that's the following map here. You do the phi I, which is this one down here like this. Then you go across this to F, and then you invert this map here, this coordinate patch here, this psi j. So you go like this. Of course, this is not defined, this psi j inverse is not defined on all of y, only on wj. So you have to be a little bit careful about how you do this. Okay, F is defined on all of x. Okay, so you can't just compose this and the inverse of psi j. You can only do that when you're sure that the image of this lands inside the image of that. So what we're going to have to do is we're going to have to restrict to the inverse image of this wj. So maybe that's here like this. And then restrict to the inverse image of this thing up here. Okay. So once we do that, if we know that this part maps to here, and this part actually maps into some part of this, whatever it is, then we know that we can apply psi j inverse to give you a map in this direction. Okay, so that's what we've done here. We've restricted the map not to all of this unit ball here, okay, but just to the inverse image of this shaded region here. And this shaded region is where this is defined. So it's the intersection of VI, this is this bit here, with psi j inverse of WJ. Okay. So that's the thing that you have there. So it's the intersection of VI with, it's not psi j inverse, this should be an F inverse rather. So let me just correct that firstly. That this is an F inverse of WJ. So once you have that, you're working inside this open set here, then this composite is well defined. And we just want this to be smooth at phi I inverse of P. And if it is smooth at that point, then we'll say that this function is going to be smooth at P. Okay, so a couple of things to comment about this. So firstly, this point P lives inside VI, but it could actually be inside a different open set, a different coordinate patch. And then what would happen? Well, that means that you would use a different homeomorphism with another copy of the unit ball. And then, well, does that change the smoothness condition here? And the key point here is that the definition of a differentiable structure insists that the transition functions are smooth. So if the transition functions are smooth, that means that it doesn't matter which coordinate patch you use. If it's smooth using one of them, it'll be smooth for the other, and vice versa. So this notion is independent of which coordinate patch you choose, and that's very, very important. Okay, so that allows you to talk about smooth maps between manifolds. Now, of course, one smooth manifold that you can have is the real numbers, the set of real numbers. Okay? And so what we're going to do is we're going to introduce a very important class of functions. Okay? It's going to be the set of germs of smooth real-valued functions on x, then they're smooth at P. Okay, so what does that mean? So basically, we're looking at continuous functions from our x to the real numbers, but they're only germs, so they don't have to be defined in some open neighborhood of this point P. And they're smooth in the sense that I've given. And the important thing is that, well, when do two germs, when are they equal? Okay, so they're equal when they agree on some open neighborhood of P. Okay, so they could have different domains of definition, but as long as two germs agree in some neighborhood of P, we'll say that they're the same germ. Okay, so now let's try to come up with a more intrinsic way of defining tangent vectors and tangent spaces. And the idea for doing this is to think dynamically in terms of motion. Okay, so the idea here is a tangent vector should be what? It should be the velocity vector of a trajectory. Okay, so we'll set this up properly, and the way to do that is to introduce the following pairing and also make sense of what we mean by a trajectory. Okay, so let's suppose you have some manifold and P is a point on the manifold, and we consider a trajectory near P. So what's that? So basically it's something like this. As time goes by, you travel through this point. Maybe something like that. That's what we'll call gamma. And this gamma will be a function from an open neighborhood of 0 to x, which basically you should think of as the variable here is time, and for different points in time, you move along this along on this manifold. And it'll be a trajectory near P, means that at 0, the trajectory will be at P. So this point here corresponds to t equals 0. Okay? So that's a trajectory, and that's what we'll use to define tangent vectors. The other thing we'll need is a pairing with germs of functions, germs at P. So this will be some sort of function defined in some open neighborhood of P. So what we're going to do is we're going to pair these two quantities together, gamma comma f. We'll pair them so that we get some sort of real number out of it. And sometimes it's good to write this out as a function of this f for each trajectory gamma. So it would be d subscript gamma is a function, and you input this f, and what's the definition of that? So what you can do is you can look at firstly gamma of t. So that's a point here. And if this epsilon is small enough, then you can evaluate f at that point. So you look at f of that. So this is some real valued function of t that's defined in some open neighborhood of 0. So that means that you can differentiate this, at least when t equal to 0. And that will be some number. And you should think of this as essentially like the speed at which this changes. Yeah, okay, it's the rate of change of this function, okay, at this point P. So that's a way you can pair a trajectory in a neighborhood of P with a germ of a function at P to get some real number. Okay, so some things to note about this setup, okay? So if you think of this as a function of f, you fix the gamma, and you look at d gamma, your inputs are these f's, which were germs of functions, and it spits out this real number. This is a derivation at P. Okay, so what's that mean? So that's an R-linear map. Okay, so it's certainly R-linear because you're just taking a derivative of this quantity here. Okay, and it's linear in this f. But the other thing is that, well, since you're taking a derivative, the Leibniz rule also occurs. So this satisfies the Leibniz rule. So let's see what that means in this case. Okay, so that Leibniz rule is telling you how to differentiate products. So suppose you have input two germs of functions, okay, and you multiply them together, then delta of fg is related to delta of f and delta of g by the usual product rule. So you have delta of f, that's some number, times the value of g at p, and you add that with the value of f at p times delta of g. And the reason why this is true is just the usual product rule for calculus. Okay, so this d subscript gamma is a function, but it's not just any old function. It's a very nice type of function called a derivation. And these types of objects occur all over mathematics. Okay, so now we are able to give our definition for what a tangent vector is. So the thing we're defining is a tangent vector here. And as I said, the basic idea for what this is it's just a velocity vector of a trajectory. So what we'll do is we'll consider all trajectories through this P. Okay, so we consider all these different gammas, and we'll identify them if they have the same velocity. In other words, to first order they look the same. But how can you tell if to first order they look the same? Okay, so let's suppose you have two trajectories, gamma and gamma prime, and they're defined in a neighborhood of P. So both of them have the value P when you put in time equal to 0. Then gamma is equivalent to gamma prime when these two functions, d gamma and d gamma prime, are the same. Because this is basically measuring what's happening to first order. Okay, that's the differential structure. Okay, you pair it up with all possible germs of functions, and if they're the same, then they should be the same velocity vector. Okay, so this is a fairly natural sort of definition for a tangent vector, and note that it's completely intrinsic. Okay, the only thing that we needed to define was this notion of smooth real valued functions here and germs of them. Once you have that, it doesn't depend on coordinate charts at all. So it's completely intrinsic, and really it matches up with this dynamic way of looking at velocity vectors, and so it's very geometric in nature and intrinsic. Okay, so that's our definition. That's in fact our first definition of a tangent vector. But actually what I want to do is I want to give you two more definitions of tangent vectors and tangent spaces. Okay, so let's look at this definition. Well, if we're going to say that these two trajectories give you the same tangent vector, when these two functions are the same, these two derivations are the same, well, maybe we should just identify the tangent vector v with this function here. And this function here, of course, you can define it in the usual Euclidean setting, and in that setting it's called the directional derivative. Okay, the directional derivative. So instead of thinking of equivalence classes of these trajectories, we talk about these derivations as being tangent vectors, and the name that goes with them is the directional derivative. And if you just look back at the formula for what is d gamma as a function of this f, you can see why it is a directional derivative. Basically, you're just looking at the values of this function along the trajectory as you go along the trajectory, and of course you just differentiate that, so that's why it's the directional derivative. So what we'll do is we'll pursue that idea of defining tangent vectors via derivations. To give our second definition of what tangent vectors and tangent space is, we'll introduce this notation de c infinity xp for the vector space of derivations as above. Okay, so one thing to note is that, of course, the set of derivations, that's well defined, and it's in particular a set of functions from c infinity xp to r, and it turns out that it's actually a subspace of that, and hence we have a vector space structure on this set here. And what's a really interesting fact, which really ties it into our other definition of a tangent vector, is that every derivation which occurs here is actually the directional derivative of some trajectory. So the derivations that you get from trajectories is all possible derivations. And that allows us to come up with our second definition of tangent vectors and also tangent space. So in particular, we have some vector space structure on the set of tangent vectors. And what is that? The tangent space to x at p, tpx, is just going to be the vector space, the set of all derivations from c infinity xp to r. And this is a really nice intrinsic definition. All you need to know is, well, what is this space of functions here? And then you just look algebraically at all the derivations from here to the real numbers. Okay, and that will give you this tangent space structure completely intrinsically. Of course, the very natural question is, well, these are functions on this set of germs of functions, and what do these functions look like? So what does such a delta, a derivation, look like? And to do that, we'll need to introduce the following subset of germs of functions. Okay, so we let MP denote the following functions. They're going to be germs of functions at P, but just the ones which are 0 at P. Okay, so it's a subset of functions of C infinity XP, and it turns out it's quite easy to check that it's actually an ideal inside here. Okay, that's just some ideal inside here, and it's quite easy to define this intrinsically, right? So once you have this set, you can just ask for this. And there's some interesting facts about this delta. So the first one is that, as you'd expect, if you try to differentiate a constant, you get 0. Okay, and we can prove that just using the properties of derivations, which I'll do in a moment. The other thing is that this is an ideal and you can square it. And it turns out that if you apply the derivation to the square of this ideal, you also get 0. Okay, so if you want to get a feel for, by the way, what this ideal is, note that every function in here can be written as a constant plus something in here. Okay, so this C infinity xp is equal to R plus this MP. In fact, the sum is direct here. Okay, so given any function, of course, you can subtract off the constant function with its value at p, and that will give you something which is 0 at p, that's inside here. And the value at p gives you the real part here. Okay, so let's go through the proof of this. It's quite nice, actually. Now, of course, delta is R linear, so to show that this is 0, you just have to show that delta of 1 is 0. Okay, so we're going to use the Leibniz property, so 1 is just 1 times 1. So you can use the Leibniz property to write this delta of 1 as just 1 times delta of 1 plus delta of 1 times 1. And of course, well, that's just twice delta of 1. And if we're in characteristic 0, of course, the only way delta of 1 can equal twice itself is if it was 0. So delta of 1 is 0, and by R linearity, delta of any constant function is also 0. Okay, what about this bit here? Okay, so what are the elements inside here? The elements inside here are just sums of products of elements in MP. So suppose we're given f and g inside MP, and we look at the product of that. And of course, we want to say delta of that is equal to 0, so the same is true for sums of things of this form. Of course, we use the Leibniz rule again to say this is delta of f times g of p plus f of p times delta of g. And the key point is, well, what is the value of g at p? G was inside here, so it's a function whose value at p is 0. So this is equal to 0. And f of p, f is similarly inside this ideal, so this is also equal to 0. So in fact, this sum here is equal to 0. Okay, so what do we see? Okay, so when we try to understand this function delta, what do we note? Okay, so it's a function from here to the reals. On this part here, it sends this to 0. So you might as well forget what it does here, and you just need to know what it does on this MP. Okay. Now inside here, you have an ideal, MP squared, and on that it's 0 as well. So really, this delta induces a map on the quotient MP mod MP squared. Okay, so that's a very important thing to know. So in other words, we come to the following proposition. Okay, so what does this fact tell us? Okay, let's suppose we pick some derivation delta inside tpx. Okay, so what can we do to that? Then we have this pairing. Okay, so given an element f plus mp squared inside this quotient, okay, this map is well defined. Delta of f is well defined because if we change by something in mp squared, okay, the delta value won't change because delta of mp squared is equal to 0. Okay. So what you get here is, given delta, you get an object of the dual vector space to mp mod mp squared. Okay. So what this is here is, suppose you're given an element inside here. Okay. You get a linear map from this to the reals. So what is the linear map? So you send this over to delta of f. And the key point is that this phi is bijective. And that's going to give our other way of defining this. Okay. So what is this? Well, you see this mp and this mp squared, they're intrinsically defined. And it's clearly a vector space as well, okay, because this is a vector space, and this mp and mp squared are subspaces, so this is a vector space. So the dual is also a vector space, okay? So you can define this tpx as just a dual of this. So before we move on, I'd also like to introduce another important notion, and that goes to extending the notion of differentials that you see in calculus to this more abstract setting, okay? So if you look at some function f, some smooth function, okay, maybe a germ of a function at p, we can talk about dfp, and it's going to be an element of this mp mod mp squared. What is it? Well, f may not be inside mp, but if we subtract its value at p, if you subtract f of p, of course the value at p will now be 0. So f minus f of p is inside mp, and we can look at the image of that inside mp squared. Okay. So when we pair a function with a tangent vector, okay, a trajectory, or more generally a tangent vector, okay, what you really pair with is just an object of this form, dfp. And that's because if you change by something in mp squared, it won't change the value of the pairing. Delta of f doesn't change. So our third definition of the tangent space actually starts not looking at the tangent space, but something called the cotangent space. Okay, so the cotangent space to x at p, that's denoted as follows: Tp star x. It's prompted by the proposition that went on before, and it's just mp mod mp squared. And the reason why we saw it's important is that if you take the dual of this, you get the tangent space. So that gives you an alternative for defining the tangent space. Is you start by looking at this cotangent space, and you define the tangent space just to be the dual of this vector space here. And that gives us our third incarnation of the tangent space to a manifold x at some point p. Okay, so now having talked about tangent spaces, I next want to introduce the notion of Riemannian manifold. And it's motivated by the following question, and that is, so we've got this notion of smooth manifolds. What about if we want to talk about the notion of lengths on this smooth manifold? So the question here is, what extra structure do we need on a smooth manifold to talk about lengths? And the answer is easy enough, especially if you keep to the dynamic point of view that I use to talk about tangent vectors. Okay. So if you want to get at the notion of lengths, one way to do that is, well, the length is given by the integral of speed. So you need to talk about speeds of velocity vectors. And velocity vectors are basically tangent vectors, or elements of the tangent space, so the dual of this. Okay. So what you need to do is you need to put on a notion of length for vectors in this vector space. At the moment, this vector space and its dual, it doesn't have any extra structure. It's just a vector space. And to get lengths in there, a metric on there, you need an inner product. So that's the extra piece of data that we need to get a Riemannian manifold. And now the definition should be pretty clear. Okay. So what's a Riemannian manifold? Okay. Firstly, we start with a smooth manifold, X. Usually it will be connected. And we're going to equip it with some more data. And what is that? For each tangent space, we're going to put a positive definite inner product on it. So that's mapped from TPX cross TPX to R. And this is for each and every tangent space. So this is for all points P inside X. And the other thing that you want is that as the tangent space varies, as you move the point around on the manifold, you want this positive definite inner product to vary smoothly as well. And the definition of that can be worked out in the same way that we defined smooth maps between manifolds. Okay, so I won't do that here, but it's very similar to what goes on there. Okay, so that's the definition of a Riemannian manifold. And the key point is that now, once you have that structure, you can, for example, talk about lengths of curves. Suppose X here is a Riemannian manifold, and we have a curve, maybe going from here, gamma of A to gamma B. Gamma will be our curve, and essentially that just means that you have some, say for example, closed interval A to B, and you have some smooth map from this closed interval to X. And let's suppose it's injective here like that. Okay, and then it's natural to ask, what is the length of this curve? And as I suggested, it should just be the integral of the speed. Okay, so let's see how we work that out. So what's the speed? So here you have this curve, and at any point in time t, right? Well, this is a trajectory in particular, and you can change the time so that this is time 0, so it's in the setting that we had before. And hence, since you have a trajectory through here, you have some tangent vector. Okay, so you straight away get a tangent vector, and we'll call that tangent vector gamma prime of t. So it's a tangent vector which represents the velocity at which you're tracing out this curve. Gamma prime of t. So it's an element of the tangent space where p equals gamma of t. So now you can look at the square length, which is given by this inner product, g gamma of t of gamma prime of t comma gamma prime of t. And you take the square of the root of that to get the speed. And just integrating from a to b, okay, from the start to finish, gives you the length of this curve gamma. So in that way, this notion of Riemannian manifold allows us to define not just smooth structure, so for example, what it means to differentiate, and also what it means for smooth functions, but also gives us a notion of distances and lengths of curves. I hope you enjoyed this adventure in pure mathematics.